So Unit 10, we're going to be talking about solubility and concentrations. When we're looking at solubility and concentration, we're going to be talking about moles in relationship to that of solution. So how many moles do we really have in a given amount of solution? So in order to talk about solubility, the first thing we need to think about is what is a solution? So I want you to think about to yourself, what is a solution? How do I know something is a solution? Have we ever heard the word solution before? Or do we know of a certain notation that could tell us that something is in solution? So when we talk about solutions, there's two real aspects that make up a solution. The first one is called the solute. Okay? Solute is the thing that's being dissolved. Some people think of this silly saying, it's solute is cute, so it's the thing being dissolved. Other thing is the solvent. That is the thing doing the dissolving. So if you're making coffee, water is the solvent, while your coffee grounds is the solute, where your coffee itself is now the solution. In order to be a solution, you must be homogeneous mixture of the solute and the solvent. What this means is that if you're homogeneous, you have the same composition throughout. If you were to drink your coffee from the top of the coffee or from the bottom using a straw, it would taste exactly the same. That's how you would know this is a homogeneous mixture. So what are some of the properties of a solution? Well, one of the first properties that we have of a solution is that solutions have no visible particles. If you're looking at your Kool-Aid, if your Kool-Aid is an actual solution, you won't be able to see the sugar inside of your Kool-Aid. Why is that? Because the particles, the thing being dissolved, the solute, is so small that it's now in solution and you can't see it. The other thing that we have here is that, again, they're homogeneously mixed, which means that there's an even distribution of the particles. So going back to my original example of the coffee, with the Kool-Aid, you would have sugar at the bottom, you would have your fluid at the top, but if you were to use a straw and you see sugar at the bottom, then you know it's not homogeneously distributed. The last type or property of the solution is that the particles do not settle out. So what this means is if I were to go and make Kool-Aid, once I've made my Kool-Aid, it stays Kool-Aid. It wouldn't be that I'd go back the next night and then all of a sudden my sugar would have settled back out of my solution and I would have had water and powder at the bottom. So again, three properties of solution: no visible parts, homogeneously distributed, and the particles do not fall out and make a layer at the bottom of your container. Phases. When we talk about solutions, solutions just are not in the liquid phase, which a lot of us think about. A solution you can actually have as a solid. Most common solid solution is called an alloy, which is a mixture of metals. We've talked about alloys a little bit in previous units. When you're looking at those, we know that alloys are a mixture of metals, such as brass or steel. You can see that brass is comprised of copper and zinc, while steel is comprised of iron, chromium, and nickel. Another type or phase of solution is a liquid solution. These are our most common that we deal with. The most common solution we deal with is aqueous, which means that you're made with water or dissolved in water. Here you can see the salt being dissolved by the water. As the water molecules surround the positive ions and the negative ions, they pull these apart, and as they do so, there is dissolving. The last type we have here is a gas solution. So the gas solution is a good example is the air in which we breathe. You can see here air is not just made of oxygen. We have nitrogen, we also have carbon dioxide and other gases. We have some inert gases like argon or some of our other noble gases, and we also have water vapor. The big thing that we're going to be looking at is when we're measuring solutions, we're looking at things first off qualitatively. Qualitatively, you can think of as quality. Okay, so we're comparing the amounts of the solute to that of the solvent. If you're looking at something that's dilute, you can think of small quantities of solute versus solvent. Dilute, very small. You can see in this container there's not too many particles of your solute per solvent. When you're looking at something that's concentrated, we have a large quantity of the solute versus the solvent. You can see in both examples our solvent is the same quantity, but our solutes are what differ. The more concentrated, larger amount of the solute versus that of the solvent. Dilute, not as many solutes versus solvent. So if you're looking at concentration of a solution, you can see that as I increase my concentration, I'm really increasing the count of my solute per solvent. As you look at A, you can see that there's only 2 molecules of your solute. As you look at B, there are more, and then C, even more. A visual representation showing you a higher concentration. So if we're looking at sample problems here, looking at the first sample problem that we have, we're looking at which of the following is the most concentrated. So if you're looking for a higher concentration, you're looking for more solute per solvent. So we're looking for a high quality or quantity of our solute, in this case our NaCl, to a low quantity of our solvent. So looking at this, we know our largest amounts are 200 grams of our NaCl. However, to increase our concentration, we want to have a smaller amount of our solvent. So in this case, our choice for this answer should be choice B. That is our largest amount of solute per amount of solvent. So let's think. How can we measure the concentration of a solution? Thinking about Unit 9, we talked about this idea of the mole. When we're talking about the idea of a mole, what we're talking about is the thought of the concentration or the quantity of something. And now in relation to a solution, we're thinking about it inside of a solvent. So there's an actual calculation that we do. It's called molarity. And we've actually dealt with molarity in our past lab when we talked about 6 molar HCl. When we talk about something that's 6 molar, what does that mean? Well, we set up the ratio of 6 over 1,000. What 6 over 1,000 milliliters means that there's 6 moles per 1 liter of fluid. In this case, our case, water. So when you're looking at molarity, it expresses how concentrated a solution is as a number. So you can see that it's moles of solute per liters of solution. If you have a 6 molar solution, then that means you have 6 moles of solute per 1 liter of solution. Also with molarity, it's the number of moles of the solute in a liter of solution. So again, we're looking at number of particles in a particular volume. If you're looking at the first 3 solutions here, we have solutions 1, 2, and 3. You can see that we have differing numbers of solvent, but our solute is the same. As we look at those and we calculate our molarity, you can see that which one would be the most concentrated. Well, if you do liters of solution, so you convert this to liters, as you convert that to liters, you're going to move your decimal 3 to the left. So we're going 1, 2, 3. So you actually have 0.075 liters in the first one, 0.2 liters in the second, and then 0.5 liters in the third. So if you were to set this up, you would have 58 over 0.075. If you were to look at your next one, you'd have 58 divided by 0.2 liters. And on the last one, you would have 58 divided by 0.5. What's the problem with this? The first thing that we need to do is we need to convert that into moles. So if you're looking at this, we're looking at NaCl. We know the gram formula mass of NaCl is 58 grams. So if you're looking at that for the mass of your NaCl, we know Na is 23, we know Cl is 35, giving us 58. So this is actually 58 grams per 1 mole. Thus, leaving us with 58 times 1 and our 0.075 over 58 grams. Nice thing is that we can leave this 0.075 alone, and we know that this grams is going to cancel with that grams. So we actually have 58 divided by 0.075. So we actually know that this is going to be 1 mole divided by 0.075 liters. So now we're at a mole to liter calculation. All of these we know that's 58 grams, so to make our math easy, again, it's 1 mole is to 58 grams. Grams canceling, 58 divided by 58 is 1, so it'd be 1 over 0.2 liters. The last one, again, we have 1 mole is to 58 grams. Again, 58, the G and the G cancel, 58 divided by 58 is 1, so you would have 1 mole per 0.5 liters. So in order to make this a real proportion, what we're going to be looking at is an actual value. So you can actually take those values and calculate that. So you have 1 divided by 0.075. And as you calculate that, you can see what your molarity actually would be. So 1 divided by 0.075, you're going to end up with 13.3 moles per liter. Then if you were to look at your next value, you'd have 1 divided by 0.2, so you'd end up with 5 moles per liter. And then in your last one, you would have 1 divided by 0.5, giving you 2 moles per liter. So you can see that you went from 13.3 repeating to about 5 to 2, showing you that there's a decrease in your concentration, as which we can see based off of the mole count of your solute to solvent. So when you're calculating these, it says, what is the molarity of the solution containing 1.5 moles in 500 milliliters of solution? So you're going to solve these pretty much the same way that we just solved that. So we need to convert to liters first. So as we convert that to liters, we know that 500 milliliters is indeed 1 liter, or 0.5 liters, my apologies. So I have 0.15 moles over 0.5 liters. And as you mathematically solve that, 1.5 divided by 0.5 gives you actually a 3 molar solution. What does that mean? Well, this means that there's actually 3 moles of your solute per 1 liter of your solution. As you look at the next example, it says, what is the molarity of a solution formed by mixing 10 grams of H2SO4 with enough water to make 100 milliliters of solution? What we have to do here is set up a simple proportion. What we want to do is our beginning statement compared to our final statement. So as we look at our first statement, it says, what is the molarity of the solution formed by mixing 10 grams of H2SO4? Well, the first thing that we need to do here is figure out, well, how many moles are in 10 grams of H2SO4. You can do this as a 2-step problem or 2 separate steps or all in 1 step. It's up to you. So just like we've converted before, you have to find the molecular mass or the gram formula mass of H2SO4. So sulfur we know is 32, oxygen which is 16, but you have 4 of them, and then you have that of the hydrogens. So as I multiply 16 times 4, we have 64 plus sulfur, which we know is 32, plus 2 hydrogens, so we have 4, 5, 6, 7, 8, so we have 98 grams as our formula mass. So I know that it's 98 grams per 1 mole. So that gives us our amount of moles. The next thing that we need to do is we need to look at our solution. So as I have 10 grams with enough water to make 100 milliliters of my solution. So now what I need to do is convert this into liters. You can either do it as a conversion or mathematically. We know milli, so 1, 2, 3. So you have 0.1 liters. So as you go through the math, you are going to cancel grams with grams. So you're going to have 10 multiplied by 1 divided by 98 multiplied by 0.1. So if you were to do the math here, and I'll erase this extra parenthesis that I have here because we just did our conversion in our head instead of mathematically. I have 10 on top, and that's in moles, divided by 0.1 times 98, which is going to be 9.8. So this is in 10 moles per 9.8 liters. I want to reduce that, so 10 divided by 9.8 gives me a molarity of about 1.02 molarity. What does that tell me? Well, this tells me that there is 1.02 moles of solute per 1 liter of solvent. Looking at example number 3, it says how many grams of KCl need to be added to make 750 milliliters of a 0.40 molar solution. So as we look at those, we want how many grams of KCl need to be added to make a 750 milliliter of our 0.41 molar solution. So we know our ending value here, so we can work backwards. So in order to work backwards, we know that X is our moles of our KCl, divided by, and we know the liters here, so we actually know that that is 0.75 liters, equals, and we have to solve for that, but we know our molarity is 0.40 moles per 1 liter. What you can do is cross multiply this, and as you cross multiply, you're going to end up with X equals, and then all you're going to do is multiply your 0.4 times your 0.75, and you end up with 0.3. That 0.3 now is how many moles that you have, which now you have to convert. So in order to convert from moles to grams, I know that 1 mole of KCl equals a mass of 74. Okay, again, K in this case being 39, and chlorine being 35. And as I add those together, you have 14 carry the 1, and you end up with 74. So now you take that 74 and you multiply it by 0.3, and you get 22.5, you should have 22.2 grams as your answer. Last question here that we have is what's volume is needed to prepare a 3.5 molar solution with 3 moles of NaCl. So we're looking for the volume. In this case, we know our molar solution, so we know our 3.5 molar solution, so moles per 1 liter. We can set up another simple proportion. So we know how many moles we want, but we don't know the liters. So we know this is 3 moles, but we don't know the liters, so we're solving for X. As you solve for X, you're going to have 3.5X equals 3. As you divide by 3.5, X equals, and we're going to use just a significant number of decimals, so 8,571 liters. Okay, so that would be the volume you have to use in order to have that molarity of your solution. Last question we have here is just a multiple choice. It says which preparation produces a 2 molar solution of C6H12O6. So we're looking for 2 moles. We know the molecular mass is 180. So we want 2 molar solution. So if you're looking at this and trying to solve it mathematically, okay, you know that your molecular mass is 180. You want a molarity of 2. So you want to have 2 moles per 1 liter. So you can kind of think about this in terms of just conceptually. So if you're looking at this, you'd have half a mole here, so this would be 0.5 moles, dissolved in 0.5 liters, so 0.5 divided by 0.5, which is 1, so we know that's not a choice. 90, again, is 0.5, and 1,000, so 1, so 0.5 divided by 1, not going to be our choice. Now we have 180, which is 1 mole, and we have 1 divided by 0.5, and 1 divided by 0.5 is indeed 2, which is our answer for that choice. That concludes the first day of notes dealing with molarity. There is some multiple choice in your notes packet, so please make sure that you do those questions, and if you have any questions on those questions, please make sure that you are indeed asking them to me.